Hello everyone. So today we will be discussing about the electrical power. So in the last class we have understood what are series and parallel combination in electric circuits. In this class we will be seeing electrical power. Now what we call specifically power as it is nothing but rate of doing work, right? Rate of doing work is nothing but your electrical power. Now is what your power. Now what happens in electricity? The work is when the work is done, the potential to do the work, we call it as electric potential. Now you know that power is going to be work done upon time, right? So what do you call actually a work done? Work done is going to be nothing but it is going to be force into displacement, right? But basic formula as we call it is nothing but the force into displacement, right? Or what we know from the definition of electric potential is that V is equals to W by Q. That is the work done in moving or bringing a charge to a point in electric field or an area of influence of electric field, or where the electric field is affecting the charge. So that is what we call electric potential. Now, can you write something from here? The work done or the about the potential difference, or I can write from here that W is equal to V Q. Right, this is your the first equation. Also, we know what uh, that I is nothing but Q upon T. Right, and we know that power is equal to work done by time. So if we divide this by time, we're gonna get it as 1 as what we will be getting. We'll be getting work done by time is equals to nothing but VQ by T, and this is nothing but power. So I can write power is equals to V Q upon T. And since this Q by T can be written as I, so I can write power is equals to V into I. So this is nothing but your electrical power. So we call this one as the electrical power. Right. So this is the expression for the electrical power. That is the rate of work done. That is the uh, rate of work done or the rate of energy in by electricity is nothing but power. That is voltage times the current. Now I want to tell you something about the heating effect of electric current, right? Now electric current in general will produce heat energy, right? So what will happen when the everything, the point here is that every device, right? Every device slash every load you are that is you are connecting has some resistance, right? Has some resistance. So what happens as it has some resistance, we can if suppose a device is connected like this, and this is your key, right? This is connected to a some source. Let us say this source is as V, and I turn on this key and this has some resistance. So always when a current flows through a resistor, right? Always when a current is flowing through a resistor, it will produce heat, right? And a resistor will produce heat when current flows through it. So this is nothing but a phenomena which we call as Joules heating effect. So what this resistance causes is that when the current is going to flow through this resistor, what will happen? This resistor will produce the heat. So sometimes what happens, suppose a fan is running. So fan is running, then the main aim of the fan is to rotate and give you the air. But what happens? There is some heating also. there is some heating also, and that is undesirable. But in all the loads, sometimes it is desirable. Let us say a heater. So in a heater, we want the more heat to be generated. So that is Joules heating is of use in that case. But what you need to know is that every device, when connected to a voltage difference, that is a potential difference, current will flow and the heat will be produced, and that will be produced due to this resistance. So how this heat is produced? Let us see. You know that power is equal to Vi, just now we derived, right? And you know that power is equal to work done by time. So if I want to find the heat, and heat is nothing but, so heat is nothing but it is in joules, that is a work only, right? So if I write work is equal to power into time, right? So I can write work is equal to Vi into T, right? And this voltage difference, you know that V is equals to IR. So I can write V as this is equal to work done is equal to I into R into I into T. Now what happens? You can know that work done becomes I square times. This is one I. So this is I square R. So this is nothing but your joules heating effect. Right, this is your Joule's heating effect. So by this formula, you can calculate the amount of heat. So you can see that whenever this heat energy, this unit will be joules, and you can see that this heat energy depends on the value of the square of the current and the resistance also. This R, right? So what happens? This heat energy. So because I am calling it as heat, so I will represent by H. That is H is equal to I square RT. So this is a formula, and you can see that the heat is directly proportional to the square of current, heat is directly proportional to the resistance, and heat is directly proportional to the duration for which this voltage source is turned on, right? The duration for which this key is keep kept on, that is the duration for which you keep your devices turned on, that will determine the amount of heat generated by that device, and it is directly proportional to the resistance. As I told you, every device load has some resistance, and this resistance will be creating heat, and it will be also directly proportional to the square. So in some numericals, examiner can ask you such questions like calculate the amount of heat when resistance value is given, or in some other forms he can ask. So the whole formula is that you need to understand this, how you derive this formula. Derivation may not be asking, but you must understand the concepts involved. That is how these formulas are derived, and what is the significance. That is the Joule's heating effect. Right. So you can see that this time duration is going to affect the amount of heat generated. Right. And sometimes similar kind of approach or this approach is taken in calculating your electricity bill. Right. What happens? You pay electricity bills, right? And electricity bills are nothing but you need some units, right? You need to pay some amount of rupees to the your electricity providing company. So what happens? So whatever the amount, how it can this amount be decided, right? How can this amount be decided? So there should be some units. That is, suppose you went to market to buy some apples, right? Then you ask them that what is the rate, right? At what rate, or what is the cost, right? Or what cost? So he will tell you that rupees something will say 100 per kg, right? So per kg is the unit. That kg is a unit of weight. So he is having there is a defined unit, and by that he is giving you the rate. That means if you buy 1 kg, it will cost you 100 rupees. If you buy 2 kg, it will cost you 100 into 2, that is 200 rupees. So similarly, we need a calculation for electricity bills also. You're gonna pay for the energy you are consuming, right? So there should be a proper systematic way so that there should not be any uh, there should be like a even fair price for the electricity you consume. So that is why what happened. We know that power is nothing but voltage into current, right? And work done is nothing but your VIT. Now let me first of all consider the units of this, right? You know that power is nothing but voltage into current. That means this is volts into amperes. So power unit can be volt amperes also. And you know that power is nothing but work done upon time. So work unit of work is what? It is joules, right? Represented by J also. So you know that power is nothing but joule per second also, right? Joule per second. And when we call joule per second also as 1 watt, right? Represented by W. This 1 joule per second we call as 1 watt also. And in your exam, sometimes they ask that define 1 watt of power, right? 1 watt of electric power. So 1 watt of electric power is what? When a potential difference of 1 volt produces current of 1 ampere in a circuit, then the power consumed in the resistor is the power consumed in the resistors is 1 watt. So he is asking such kind of definition, and from this you can know that work done is nothing but now VIT. That means this unit is volts into amperes into time. So this is nothing but volt ampere second. So work done unit can be volt ampere second, or you can also say that volt ampere is nothing but your watt, right? It is nothing but your watt. So it is what? Second also, right? So sometimes what happens in my multiple choice question, he can ask you some questions like this, right? Watt second. And what happened? You can sometimes what happens, this watt is not a very big unit, right? It is a small unit in terms of the electricity we consume, right? So we define further another unit which is nothing but kilowatt hour. So you know that I told you just now that it is VIT. So I gave you that this is watt second. So this is a smaller. Suppose what I do, I write this in, I want to write this in say kilowatts, right? And I second say I in for second I want to use such as say hours, right? So this is quite a bigger unit. So 1 watt second is what? 1 watt second is what? Is nothing but 1 volt into 1 ampere into 1 second, right? So suppose I wanted to convert into kilowatt hours. So how it gonna be, right? Or I can if I want kilowatt hours, what is kilowatt? It is thousand watts, right? And what is hour? Hour is nothing but 3600 seconds, right? So if I want to write 1 kilowatt hour, what I will be writing? It will be I will be writing it as 1000 watts into 3600 seconds. So this is nothing but 3 zeros this, and 36 into 10 to the power 5 watt second. Or because scientific notation I write point after first significant digit, so it will be 3.6. If I am writing, I can write it as 10 to the power 6 watts per watt second, right? This is your 1 kilowatt hour. Understood? Or watt second is what? Watt second is what? It is nothing but it is what is what? It is nothing but your worked upon time. This is joule per second, and it is second also. So I can write watt per second is watt second nothing but as joules also. This is 3.6 into 10 to the power 6 joules, right? So the meaning is that this much is how 1 kilowatt hour is equal to this many joules. So you can see that joule is not a very big quantity, and we calculate like this. And this is nothing but the unit of electricity, right? 1 kilowatt hour is what? It is the unit of electricity. Now by this unit you will be paying. So the rate for this 1 kilowatt hour will be something say X rupees, right? So number of kilowatt hour you consume, you multiply that with the number of your units consumed, you will get the billing amount. So this is how roughly you can understand how billing is done. Now I want to gives some information or tell you something about a device which is called fuse. Right? So first of all, you need to understand this, that this is a safety device, right? It is a safety device, and it is meant to protect your appliances or whatever your devices, every such as your household appliances, right? Or whatever in general you are connecting to the electrical socket, it is meant to protect your devices. So what happens, sometimes we represent the symbol of fuse such as like this, right? Let me tell you. So like this you are representing the fuse, right? This is your fuse symbol. So what happens in a circuit, let us say this is your resistance is connected, right? And a fuse is also connected in the circuit, right? And this is your key. Suppose this is a circuit. So what will safety device, what will fuse do? It will protect from overcurrents, right? So its principle, and also you need to understand that its principle is based on Joule's heating effect. How the principle is based on Joule's heating effect is that this is made of a alloy, right? Whose melting point is right. Melting point is just near the rated current, right? The current which is, let us say, through this your load only 5 ampere is the limit which should be flowing in this. But due to sometimes what happens in power, in this power systems and all, sometimes a current more than 5 ampere can be observed. So if that is the case, suppose 5.5 ampere is flowing in your resistor, then the amount of heat generated would be I square RT. So if the rated current was 5 square, rated heating is 5 square RRT, that is 25 RT in your device. Now due to some reason this becomes 5.5. So now the heat will be 5.5 square RT, which will be more, and due to this heating so much, this device will get damaged, right? So to protect this from the damage, what we do is that to protect this device from damage, what we do, we are going to place a fuse. And what this fuse will do, this melting point of this, it will be made of a wire. That is why this symbol is like that. It is made up of a wire which is made of an alloy, and its melting point is about the rated current only. So what happens, whenever the current more than rated current is going to flow in this circuit, this will melt due to the heat. And as this melts, this will become melts, and it will melt down, and the circuit will become now open, right? Circuit will become open. And you know that for electric current to flow, we need two conditions. One is potential difference and one is closed path. Since this circuit becomes open, there is no closed path now. No closed path, that means no circuit. So what happens, current will not flow and your device will be now safe. So this is how a fuse is used, right, to protect from overcurrents, and is based on Joule's heating effect. Nowadays what is happening, in case of fuse, we are now using MCBs, which is nothing but your miniature circuit breakers. This is also the meant for the same purpose, but the principle involved of working is different. What happens, whenever an overcurrent flows through this your circuit, in case of fuse, you are now today having MCBs, and what they do, there is a relay kind of mechanism there. What happens, whenever there is overcurrent, what will happen, this MCB will trip. That means suddenly if there is an overcurrent, the MCB will automatically, there is a spring mechanism that will automatically, the switch will become open and it will trip. So trip is meaning is what, the circuit becomes open, and then no current will be flown and your device will be now safe. So this is how MCB is used today in place of fuse. Right. So this is how you can understand how a fuse works and what is Joule's law of heating. And let us now take your, for example, your domestic supply system, right? Or the electricity you are uh, receiving in your household. So there are currents are of two types. You need to understand that. So one can be your AC and one can be your DC. So AC means alternating current. The full form is alternating current, and DC is direct current. Right. So the difference between these two is that in alternating current, suppose I always draw the graph of currents like this because I take one value of current. Suppose I'm taking I as 5 amperes. So it is 5 ampere at every time. That is a straight line. Suppose this is a time axis and this is the current. So it is a 5 ampere. Suppose I'm taking saying 10 volts is the voltage which I am applying. So it means that if it is a direct current, so this source is also 10 volts. Let us say this axis is voltage, this time. So it will be at every position of time, at every position of time, at every position of time, the voltage is 10 volt only. At every position of time, the current is 5 volt. This is what direct current. It remains, it doesn't change with change in time. But what happens at your home, right? You are receiving AC. Okay, this you need to understand. And there is a, voltage or the level of voltage which is fixed, and it is also separate category of voltage which is the RMS, which will be learned in higher classes. And that rating is nothing but you need to, for now, just remember it is 220 volt, 50 hertz. Now you see there is a term of frequency. This is how we represent AC power which is received in your home. So this is a different kind of terminology or different parameter we use for AC circuits, which you'll be learning in higher classes. For now, you focus on this 50 hertz. This is the frequency which we are using in our country, and 50 hertz means that it is universal throughout the country, right? The same standard we are using every year. And 50 hertz, you can understand that whenever there is a term of frequency, it means something is changing with respect to time. So that is why when you plot the time with this current, suppose generally it is of a sine wave, that is with time this current is varying. Like you can see that every interval of time, at any time you see the current is changing like this. It is not constant. This is what alternating current. Alternating means it is changing, and it is changing with respect to time. So this kind of a current which we are receiving in our homes, which is AC, right? And it is what alternating current which is changing with respect to time. We are not receiving the current in our homes which is this form. It is a constant current. This is a direct current. This is where, this is generally in your dry cell, right? That is the pencil cell you are using, and batteries are there. Then this is direct current there, right? The small batteries which we are using, right? The pencil cell, that is all, that is DC. But the home sockets, whatever power you are getting, it is AC. Now, let us understand the concept of earthing also, right? You know that in your some of the 3-pin sockets, you have a wire like this. There is a much bigger pin like this, and this is nothing but your earth pin or earth pin, and this is nothing but your live and neutral wire, or sometimes we call this live as phase wire also. So this is the pin or the wire in which the current will be flowing. Suppose this is the resistance, right? And this is your this so through this resistor, we have two ends, right? Like this, suppose. So one will be phase from which current is coming, right? That is phase, and other point is neutral. So this is how you correct in the circuit, phase and neutral. So always you can see that everything you will be connecting between this phase and neutral, right? And everything will be connected. And what you can see is that in general, in your homes, the combination which you are using, it is nothing but this parallel combination. Why parallel? Because suppose if I am using two resistors like this, something happens to this, right? Something happens to this becomes faulty. So this will not work. But what will happen now? The current will have still a path to flow like this. So that this load will be working. Now what happens? Suppose there is a series combination, right? Suppose there is a series combination. Now what will happen? In series combination, suppose what happens, since there is only one path for the current to flow, what will happen? Suppose current starts flowing from here and this becomes faulty. Then what will happen? Since this becomes faulty, this if this becomes an open circuit, so due to this faulty condition of this load, this current won't flow and this will also not work. So that is why we are using parallel combination first of all. Okay. In our power system, we are using in domestic power supply, we are using parallel combination, right? And let us continue to our discussion of that earth and neutral. So this was your phase, or I can say this is a live wire, and this was your neutral wire, right? And this is your earth. So why this is used? This is a much bigger pin. So what happens whenever you are placing the socket in the, suppose a metallic surface is there, right? Metallic surface is there in your device. Let us say sometimes generally coolers, right? Right, refrigerators. So in these devices, what happens? There can be some charges, right? Some residual charges which are on the surface of this you can say this devices. So what happens? This earth is connected to this is in your home is connected to a proper earthing mechanism which is below your house, because before building or constructing a house or some or a building, this earthing mechanism is done. What has happened? There are some layers and some uh, thing is done. Sometimes in general, a rod, metallic rod connected to this earth is placed and put inside the earth in the ground. So what happens? Whatever these extra residual charges are on the body, you will plug the socket into this, and that's why this earth pin is bigger. It is longer and bigger, thick than these two. So what happens as you place this into the socket? First contact comes through this pin only. As you place the plug in the, you can say, socket, what happens? The first contact is made by this your longer pin, which is earth. As soon as this earth gets connected with this socket, these extra charges will first flow through the earthing mechanism and they will flow to the ground. So what will happen? These charges won't flow through you. That is, the current won't flow for you, and you will be protected from the electric shock, which can be fatal also. It can take sometimes your life also, and that is why this earthing, what it does, it will allow these charges to flow through the uh, your ground safely. So that is how you get protected. So earthing is done for your protection also. Use is also for the protection of device, right? So this is how the working of earth or the grounding is done. So this is all about this chapter. So in the next class, we will be discussing some of the numerical questions and conceptual questions related to this chapter, and then we'll continue forward.